So what I'm going to try to talk about today, and I'm going to take about 10 minutes because I know time is a constraint here, is an alternative approach to doing analyses, day-to-day analyses that we do for quantitative analyses that we do for some of our work. In particular, I'm going to focus on a method called quantile regression. Interestingly, quantile regression, let me just make a slideshow here. Can you see my screen or no? Or
Yes.
can you see?
Presenter view,
The presenter.
so we can see all the slides.
Okay, so then we probably don't want to do that. How about this?
Perfect.
Which is not a new technique. It's a quite old technique. I think it emerged sometime in the late 60s, early 70s. At least began its use in at that time. But it's quite an interesting technique. Before I go into quantile regression, I want to just talk a little bit about what we use most of the time. And that's the ordinary least square method. This is something that all of us have been trained on. It's a method that's quite easy to use. The issue, it's really the workhorse of a lot of kind of substantive research that's done. It's the workhorse of modeling, if you will. The problem with the least squares is that it has a lot of assumptions that are embedded in it that we usually gloss over. I mean, at the beginning, when we were kind of out of graduate school, we paid very close attention to it. But with time, you kind of put those to the side and you say, "Oh, this method is really robust to violations of these assumptions." So issues like linearity of parameters, homoscedasticity, the fact that you have a unique variance rather than multiple variants for different subdistributions within kind of the outcome of interest. And then the issue of outliers, which in some cases are not critical to kind of understanding the problem that we're trying to study, but in many other instances, they're really fundamental to trying to understand the problem and at least kind of theorize about it. So as I said, in many cases, these methods are abused. The models are misspecified, the assumptions are not met. And the argument that's used is that these methods are less problematic in the context of violations of assumptions. One, again, issue that is dominant in the way I understand least squares, at least, is that it's focused on a specific quantity of interest, which is the average, the mean. And that's not always an interesting quantity to understand. I'll talk a little bit about other quantities that are at least interesting for my type of research that I do. So OLS really fails when you have clear violations of distribution. So when you have bimodal or multimodal distributions, we have multiple peaks in your distribution. When you have very skewed distributions, one of the kind of main outcomes that I attempt to study are health expenditures, disparities in health expenditures or healthcare use. And those are really skewed skewed outcomes. You have a lot of people that use very little, but these tend to be the most interesting people to study, the super users in essence. Those are the people that consume most of the healthcare resources. And of course, in my case, some of these outliers tend to be interesting to study. Under the OLS, applying least squares can lead to biased and inefficient estimates. So enter quantile regression. In quantile regression, from a substantive perspective, what you're trying to do is reformulate the way you think about specific quantities that you want to study. So instead of saying, I want to see what the mean spending relative to a particular covariate or set of covariates is, you say, I want to study what the lower tail or the upper tail of the distribution looks like and how it relates to a set of covariates. Here I provide a very simple example. Health spending is particularly interesting to study for people who are healthy and also for people that have catastrophic or very high spending. Those are the individuals that from a policy perspective, you probably want to focus on. Also, this relates to a lot of theoretical work about elasticity of spending in terms of healthcare use. And I know for a fact, based on years of modeling these outcomes, that the OLS assumptions are not really warranted, and in fact can lead to biased and inefficient estimates. The mathematics behind quantile regression are it's somewhat hard, but at the same time, they're intuitive. If you remember from your stats 101, when you studied least squares, all you're trying to do was to use a loss function. So prediction relative to actual observation, right? And what you want to do is minimize the squared of the errors between the minimum, the line of fit, and then the distribution of these actual observations along the predictor. So most of the methods that probably you're aware of, and quantile regression is one of those methods, attempt to use a different loss function. So instead of focusing on minimizing the sum of squares, in some instances, you focus on the absolute error loss. So instead of using squared, you use absolute value. And there are different ways by which you can characterize the loss functions. The one intuitive way, at least the way I tend to think about this, is that these loss functions have a common thread, and that is you attempt to provide a weight for different observations that can lead to kind of different prediction models. So the least absolute deviation, Huber robust, bounded regression, where you kind of move out some, or at least weight to zero some of the observations that exist of the outliers. Those are possible techniques. And quantile regression is kind of an alternative to some of these methods. You also have seen other approaches. Many of you probably have used generalized linear models before. And some of you probably have modeled meaningful zeros relative to an actual distribution of a continuous outcome, and then brought the two expectations together. And maybe some of you mixture modeling, where you assume that there are unseen sub-distributions that exist in the data, and you try to kind of extract these sub-distributions and model them. So when to use quantile regression? Where from my view, I think the substantive reasoning for using quantile regression is what drives my interest. And that is, as I mentioned before, that I'm interested in the complete characterization of the conditional distribution rather than just focusing on the mean. And then it's a pretty interesting method because it allows it really absorbs these violations of assumptions, particularly the violation of homoscedasticity, that different kind of sub-distributions that exist have different slopes, and that slopes in and of themselves are actually interesting. I'm going to skip this math here. A warning that comes with using some of these complex techniques is that they are complex for a reason. The math behind them is a bit more sophisticated. The properties are less easy to understand than with standard methods like the OLS. And then in many cases, they're computationally intensive, but nowadays that's not a big issue. Most of us have kind of quite powerful computers that we can use. They rely on bootstrapping techniques. At least that's the method that's most adopted to generate standard errors and create confidence intervals, which allow you to make inferences about the specific parameters that you're trying to study. There's also a potential for precision in these estimates. Of course, data sparsity of these tails of the distribution is going to be a very problematic thing, particularly when you have small sample sizes. Okay, so this substantive example is just to kind of give you an idea of what you can do with quantile regression. Most of us, again, tend to focus on the mean. I'm trying to argue that there's values or parameters that are a lot more interesting than just focusing on the mean value, and I'm going to show you how to do that. So for this particular case, I'm going to look at total health expenditures as a function of self-reported health, insurance, age, race, ethnicity, and then use of expensive healthcare resources emergency departments and hospitalizations. And kind of the substantive driver of this, the hypothesis is that that we have disparities in health spending, and those disparities really extend beyond just the average value, that those disparities are more likely to manifest at the tails, particularly among the high-end users of healthcare. You can see kind of the violations that I talked about in terms of the distributions. These are called violin plots, and what they show you is that the distribution here is not normal. It is really, really skewed. Very few people have very high levels of spending, and that the skew of the distribution, the centrality of the central point of the distribution varies across these different racial and ethnic groups. You can see it here in this table. When you look at the 1st, the 5th, the 10th, the 25th percentile, you can see that there are variations in the differences between groups that exist at each one of these estimates, if you will. All right, so how do I do this? Well, luckily, you don't have to kind of do things from scratch. Most of these techniques are already boxed into many of the software that you're familiar with, the QRAG or the QuantRag in R and Stata. In this particular case, I use Stata, and what you see here is the estimates of the OLS, which is the mean estimate, versus the 5th, the 10th, the 25th, the 50th, the 75th, the 90th, and the 95th percentile. This is kind of hard to absorb as a as a table. But what you see here is that the 2,432 estimate that you get from an OLS is actually a very reduced version of the disparities reality that exists between these groups. And here I'm focusing on Hispanics, but you can also apply it to Blacks or these other individuals, and that there are variations in terms of the differences between the groups, right? You notice that for Hispanics, for example, compared to, let's say, Blacks, the disparities between Hispanics and whites at the highest end of the distribution, right? The very kind of end tail of that distribution is a lot larger for Hispanics compared to Blacks. Now, obviously, this is a function of the covariates that I use in this. But again, the interpretation of these estimates provide for a richer characterization of the data that you have. These will be interpreted here. It's interpreted as a dollar estimate. So in OLS, you would say Blacks compared to whites on average spend $492 less on health expenditures, whereas here you say the kind of the 5th percentile of the distribution, so the lowest 5th percentile spends about $160 less compared to whites. And if you want to interpret the 95th, you'd say they spend about $1,000 less. Now, obviously, you've heard me talk about this before, that the tables are a bad way of representing things. I prefer to show things as graphs rather than tables. And what you see here is, if you just focus on the OLS, your entire interpretation is going to hinge on that blue line that's right in the middle here. That is the constant that you're going to talk about when you're trying to interpret your results. Whereas when you use quantile regression, you have a much broader view of this distribution. You can see what the effect of being, right, of age or a female or of being Black or of being Hispanic is for each one of these percentiles. And obviously you can see that if you're interested in disparities, you'll notice that the disparity becomes more and more aggravated across all racial and ethnic groups as you move, right, away from kind of the bulk of the distribution in terms of healthcare use towards the very high end users of that distribution. Okay, so you can do the kind of the same things that you would do with the standard OLS, where you can kind of sequentially adjust and see the impact of this adjustment on your estimates, right? You see attenuation in the estimated parameters through, here adjustments for a select set of covariates, but here through additional adjustments for ED use and hospitalizations. And what you notice here is that although the difference, right, between Blacks and whites, I'm just going to give an example here, at the 90th and 95th percentile tend to be such that blacks spend more compared to whites in unadjusted models. That difference is completely flipped once you start adjusting for some of these covariates, and blacks really become disadvantaged. And what that says is that blacks are more likely, at least my interpretation of it, are more likely to be high users of emergency departments and hospitalization. Is that level of use that explains this flip, right? So this is a confounded estimate compared to what you can get after fully adjusting for these covariates. At the end, this is going to be given to Deborah. I provide accessible readings. These are things that I can read at least. And then you have some more complex things that include higher ratios of math to words. There's a book length treatment by the guy that really made this method available to the masses. And then a more advanced treatment that was published in 2017 that kind of expands beyond just, the cross-sectional to talk about, how you treat things when you have missing data, how you treat things when you have longitudinal data, et cetera, et cetera. So I'm going to stop here.
Fantastic. Any questions for Wasim?
Yeah, I don't have any questions per se. I think the hard part for me is to figure out, at least with regard to the work I do, when would this be appropriate? I can definitely see it in terms of healthcare expenditures, but in terms of some of the social psychological stuff that we do, just trying to figure out when is looking at the distribution that important. And let me mention, I had a hard time understanding the graphs, though as you explain them, I start to see it a little bit more. I think personally, maybe many of us, but definitely I need a lot more help looking at graphs. A lot of times when I'm explaining interactions, I do better looking at percentages than at graphs, but the graphs give you a more accurate picture of what's going on.
Thank you, Robert.
So Robert, just
You want to talk about a little bit your thoughts about social and psychological variables and when you might use this?
So let me just give a kind of a simple example. If you're looking at depressive symptoms, which is potentially something that you might use, a lot of people, what they end up using instead of, let's say, modeling the continuum of the CASD, they say there's a threshold. And if you're above that threshold, then you consider depressed. And if you're below that threshold, then you're not depressed, which is a very, in my opinion, at least, it's a very bad way of doing things. I think in this particular case, it's potentially more interesting to look at these percentiles, these quantiles, and say, what does the 15th percentile of the population look like? And what determines, what are the covariates? What are the associations with some of these predictors that are of interest? Now, it's probably a bad idea to just focus on one percentile. I think it's much better, use of these methods to kind of model the entire distribution rather than just focus on a specific quantile, because it gives you kind of the stretch of disparities if that's one of the issues that you're trying to understand.